from Hyperlane. Can you hear me well? Yeah? Okay, cool. So today we have the modular data availability panel. So we are with some of my favorite teams, Celestia obviously. We have Avail, we have Espresso, and EigenDA. So if you guys can quickly introduce yourself.
Sure, I guess I'll start since I'm right next to you. Hi everyone, my name's John. I'm with Celestia Labs, one of the co-founders of Celestia. Primarily do protocol research, specification work, do my best to help the engineering, the protocol engineering team make improvements, etc. to the protocol, and occasionally I should post on Twitter.
Hey, my name is Benedikt Bunz. I'm one of the co-founders of Espresso Systems, also the chief scientist. So I work on sort of the hard technical problems that we're facing, and including trying to design our DA solution and what that looks like and how it integrates with other systems. And yeah.
Hi everyone, my name is Dan Mills. I'm the head of product at Avail. I help the team go where it needs to go, kind of do whatever it takes. Yep.
Hi everybody, I'm Sriram, founder of EigenDA. EigenDA is a mechanism that allows anybody to borrow trust from the Ethereum core protocol so that anybody can build new decentralized protocols on top of it.
Good. I feel there's like different level of noise on the mic, but I don't know if it fits me or, well, anyways. Cool. So I don't know if I introduced myself, but I work at Hyperlane and interoperability solutions. So we work very closely with Celestia, we work very closely with EigenDA, and we are in collaboration with Espresso and Avail. So first question, what is the need for modular data availability? And a question for myself, can we please call it data publishing? Because first of all, it's hard for me to say it. And second of all, I think it makes more sense. What do you think about that?
I guess I'll go first. I like data publishing because it has the acronym DP, which is memeable. It is also better. It is also more accurate than data availability. Because, I guess, small tangent here since we're talking about the subject. Any blockchain like even Bitcoin provides data availability. It's more about being able to verify data availability using sublinear work, which is different than data being available or not. It's the verification of that property. So I guess to answer your question around why the need for these data availability layers. The reason for this, and this was kind of elucidated in Mustafa's paper, Lazy Ledger, is that by decoupling the process of data availability from the rest of what a blockchain would usually do, namely execution primarily, you don't have to do execution on the most base trust layer, which is the consensus layer. And by not doing so, you can therefore use the resources that would have been used for execution. You can use them for just straight up data availability and nothing else. This allows the basis of trust layers to kind of maximize the data availability it can provide, and therefore maximize the data availability available to all applications that build on top of it in higher layers.
I mean, I actually kind of disagree with the fact that data publishing and data availability is the same. So one is the process of I just broadcast the data, or I view data publishing or data broadcast, which is what normal blockchains do. You're totally right that any normal blockchain does that is broadcast the data to everybody. And this is especially true for blockchains that execute. So something like Ethereum, in order to verify that an Ethereum block is valid, I need to have the block in order to show that the block is valid. It turns out that for something like a rollup, or in some scenarios in layer 2s, it's okay to have something weaker. So what if I don't have the data, but I'm ensured that the data is available? I mean, this is a little bit what you're referring to as the light client sort of problem, but it's also, for example, what I can do is that even the full nodes, I just split the data amongst the full nodes. But I do it in a way that even if, like a portion of them goes offline, I can recover the data. Now the big difference is that, say I have a block that is a gigabyte in size, and I have 100 nodes, then I don't need to send out 100 gigabytes anymore, but instead each node only gets, well, 10 megabytes or something on the line. Maybe they get 20 megabytes. So the total amount of data that I have to send out is significantly less if all I need is data availability, right? If all I need is to show that the data is recoverable, I can actually sort of asymptotically be much more efficient than when using a normal blockchain where I broadcast the data to everybody. So the way that I would phrase it is that data publishing gives you data availability. This is 100% true. It's something sort of stronger, but it's also more expensive because it means that everybody has to have all of the data. So this is, I think, one of the core why we can even do better, like fundamentally do better with data availability.
Do you want to answer?
Yeah, unfortunately, data availability is a word that a lot of people use, and the definition is a bit hard to parse. Yeah, generally, data availability is the ability to know that data was published, so that new blocks can be verified on the chain. And data availability focused solutions have a variety of different characteristics, but I think to me, like a particularly important one is the ability of a client that doesn't consume all the data to be able to verify that the data is being published. So it's like the being published is the part that's very hard to convey with a word like publishing or even availability. I
mean, it's really about the data being recoverable, right? It is about the fact that in case something bad happens,
that's right,
I can recover the data.
Yeah,
I think
and
it's,
that's what we mean by available, right? Is that it is available right now, it is recoverable right now.
Yeah, I mean, all of these terms, obviously, they're super confusing.
Yeah. So I think like for better or worse, the industry has converged on this term DA, and I think yeah, it is what it is. In terms of why it's so important, I mean a couple of reasons. One is that as a strategy for scaling Ethereum, rollups have been the tool of choice that we have been working on since like 2020. And that's clearly visible today. There's dozens and hundreds of rollups coming, and that is the tip of the iceberg. There's many more coming, thousands of rollups. These rollups are very block space hungry. They need to post their data somewhere so that their execution can be verified or their liveness can be guaranteed depending on the construction of the rollup. And so Ethereum's block space is very limited, and so these other solutions have sprung up that allow for like off-chain data availability. But they're useful beyond that as well because some of these solutions come with additional features depending on how the rollup is constructed. So for example, Avail provides light clients with KZG commitments that can be verified as like validity proofs. They use data availability sampling. And these are benefits that chains that deploy on Avail can obtain. So different solutions have different pros and cons. But generally, there's a scaling aspect to it. There's an additional functionality of like being able to verify from a light client, like on a user application running on a phone, for example, being able to determine the correct state of the chain. And so, yeah, there's a lot of research that is going on to push blockchain's technology forward.
I'm not going to get into the terminology war here, but I'll just add a little bit on how we think about data availability. EigenDA is an Ethereum-centric data availability system. What do I mean by an Ethereum-centric data availability system? When you're building a system, you have to start with what the goals of the system are. And when we started building EigenDA, the main goal was rollups on Ethereum don't scale. How do we make them scale? And the only reason they don't scale is that you can't write data. Compute is offloaded. People can make proofs of computation and then submit them to Ethereum. You have ZK proofs, you have optimistic proofs, all of these coming up. How do you make sure that the data required, the inputs and outputs of such computation, need to be made usable, available, retrievable, publishable, whatever, to everybody? So that was the goal. So this lets us make very different trade-offs than other systems. For example, we don't have a consensus protocol. Why? Because Ethereum already has a consensus protocol. Why should I do the same thing that Ethereum's already doing? No consensus protocol on EigenDA. What this means is now you have various degrees of freedom to optimize the system. So because we're an Ethereum-centric data availability layer, one of the things was, how do we use the native operator set of Ethereum itself to do data availability? How do you use the native stake of Ethereum itself to do data availability? How do we try to make sure that when building a new system, this new system doesn't have additional stricter assumptions of, say, censorship? For example, what happens if you're building a chain is most of the chain protocols are leader-based, which means there is a leader who makes the block, sends it to all the nodes. So when you have a leader, the leader becomes a censorship choke point. If the leader forbids you from publishing your block doesn't get published. The leader becomes a censorship choke point. The leader becomes a throughput choke point. All data goes through a leader. The leader needs to know all the data. So leader becomes a throughput choke point. So our design aesthetic is no node ever needs to touch all the data. No node ever needs to touch all the data. So if you're a rollup, you can directly commit data into EigenDA, publish it back onto Ethereum, publish the attestation. EigenDA, eigendata availability, or eigendata attestation. Attestations are coming into Ethereum that the data has been made available. And now you can actually scale the system massively without inducing any new censorship choke points. Because there is no leader, there is no off-chain censoring. You can directly write data into the EigenDA nodes, get the certificate, put it back on Ethereum. So this is the basic premise, and that's why I think we're able to scale without adding too many new trust assumptions on top of Ethereum. Our goal is to keep scaling EigenDA to the theoretical limits. On Ethereum, what are the theoretical limits? I think Benedict alluded to them a little bit. On Ethereum, you have 1 million validators, each of them staking around 32 ETH. Now, if you have 1 million validators, each of them have like 2 megabytes per second. That's the node requirements to participate in Ethereum. If you have 1 million nodes and 2 megabytes per second, you multiply these two, we're talking about terabytes per second. That is the theoretical scale that you can achieve if you build a hyperscaling data availability system on Ethereum. So our goal is to scale the system to these limits. Right now, we are on testnet at 10 megabytes per second, not terabytes per second, far away from the theoretical limits, but still far better than existing systems like Ethereum out there. 4844 right now is tens of kilobytes per second. So that's just to give a context on how we think about EigenDA.
Thank you. I'd be curious, John, because Celestia is actually the only one live, if you can give us a little bit of the design principles behind Celestia.
Sure. That's a very broad question.
To answer a little bit what EigenDA just said, like the differences and how what's the consensus. To explain a little bit.
I see. Okay, so I guess a lot of what Sriram said was, I guess, pretty. It's pretty good design direction in the context that one of the things that you want to do is one of the optimization functions you want to have is to minimize the maximum amount of work that someone needs to do to contribute security to the system, which kind of maybe leads us to talking about what is security, because one of the primary design goals of any scaling system or whatever in the blockchain space, security has to be part of your design considerations. So there's kind of, the way I think about it is there's two facets of security. One of them is people or entities, actors, whatever, posting some sort of collateral, posting some sort of bond. And this kind of underpins the economic security that you will often hear that a protocol provides. One example of this is, let's say, in Bitcoin, you can say, it's secured by its hash rate, measure the cost of hash rate, et cetera, Ethereum ultrasound money that Justin Drake likes to talk about and the security flippening. On the other hand of Ethereum, proof of stake protocols, you can talk about the value, the monetary value of whatever the validator set is, the staking set. So on Ethereum, I don't know how much it is. It's like, what was it? Sure, probably knows. It's like $10 billion, $20 billion? $10
billion.
10 billion. Okay, there we go. So it's like $10 billion is securing the protocol. So that's 1/2 of what I consider to be security. And unfortunately, a lot of people kind of stop there. There's the other half, which is there needs to be some set of actors that can hold these bond posters accountable and penalize them. In other words, slash their bond. And in the absence of that second set of actors, sure, people can post as much bond as they want, but if that bond is never at risk of being slashed, then it's not actually security. They're just dead weight, right? They're just being economically inefficient. So you really need that second set of actors. And part of kind of the design principles and optimization metrics for a lot of protocols that, or like I guess the Ethereum and Bitcoin ethos, and also what Celestia has, and this is not many blockchains have this principle, is to make that second set of actors make the worst case cost someone in that second set of actors, the people holding the bond posters accountable, make the worst case cost as minimal as possible. So in the example of Bitcoin, their security model is full nodes. You run a full node, you can hold the miners accountable. There's some issues there in terms of the fact that you have to run a full node because they don't have fraud proofs and they don't have data availability sampling, et cetera. So you have to run a full node. So the worst case cost is running a full node, which is not great, and that kind of limits some of the throughput they can achieve in order to minimize that cost. The way Celestia does it is it has data availability sampling, it has light nodes, et cetera. But one key element of being able to penalize the bond posters as being able to slash them is being able to detect faults. And kind of echoing what Sriram said around how you would design these secure protocols, is you want to have a case where there's never a need for one node to fully download all the data. But in my opinion, the important thing is there should be no need for a node only in the second set of actors to not have to do that. It's much, much less important for a node in the first set of actors to need to not have to do that. Because they're the ones providing the bond, but they're not the ones holding anyone accountable. They're the ones being held accountable. And it's, given the fact that the cost of their collateral is on the order of $10 billion, it matters much less that they have to spend slightly more money on running a slightly more powerful computer. Like, okay, $2,000, lots and lots of people can buy a $2,000 computer. We're not talking about a data center here. And you can achieve Visa level scale with that kind of computer, right? Like, with 100,000 transactions per second in the grand scheme of things is not actually like a huge amount of, it's not actually a huge amount of transactions per second. Like modern computers can do lots of operations. So kind of one of the core design principles of Celestia is to minimize the maximum amount of work someone needs to do to be in the second set of actors, the people who hold the first set of actors accountable. And the way we do this is we have this notion called this type of node that we call partial nodes. These are kind of the most expensive nodes you would need to run to provide security to the network. And they only need to download and process, in the worst case, a sublinear amount of each block. So it's asymptotically strictly better than a linear amount of work. Hopefully that answers your question.
It does. Do you want to say something?
This has been really good. I think, we've been on so many DA panels and talk about the same boring stuff. Now we're getting to something interesting, so I'm going to take it up. So the first group of actors who are actually providing consensus security, we think also needs to be decentralized. Why is this? It's because the first group of actors are the only ones who provide censorship resistance. censorship resistance is a non-accountable, censorship is a non-accountable fault in John's model. So that's one of the reasons it's better to have the first group of nodes also be more decentralized. But I kind of get the broad principle that John just alluded to. I just want to add one more thing. Any system that has erasure-coded commitments supports data availability sampling out of protocol, out of your own will. If a system has erasure-coded commitments, you can go and sample the data, the one chunk or a few chunks that you want relative to that commitment. So all the protocols here can support data availability commitments or sampling, because once you have an erasure-coded commitment, you can just go and sample, ask for just that chunk, and then retrieve it. It doesn't have to be enshrined in protocol to actually do it. So that's why we deprioritized building data availability sampling into our protocol, because it can be built out of protocol. Any of us here, if there is a protocol which has erasure-coded commitments, can build a sampling system on top of it. So our design aesthetic is what needs to be enshrined in protocol has to be built first, and what can be built out of protocol, there is a larger ecosystem that can kind of work towards it. The other reason we didn't prioritize it is on Ethereum. Ethereum itself cannot do data availability sampling, so you are going to take a trust assumption on the group of nodes that are actually providing data attestations. So these are the reasons we have different sets of priorities. And I think, just to add one more thing to Celestia versus EigenDA, Celestia was built as what is the minimum viable blockchain, right? What is the minimum viable blockchain that can actually scale? Is a very different starting question from EigenDA, which is, what is the minimum viable add-on to Ethereum to make Ethereum scale? So different questions, different answers.
Can I add something? I think very interesting discussion, and I agree that having sat on all these panels, this is like actually a very different one. Oh, is it on? Hello. Okay, so I just wanted to add a bit of context here that there are a couple of different aspects of data availability. Like one is on the publishing side, so accepting data, erasure coding it, the publishing part of it, and that does need to be censorship resistant. We take different approaches to do that. Celestia and Avail, we have blockchains. In the case of Avail, we support up to 1,000 validators, and so that I think is a pretty efficient, like a strong way to provide censorship resistance. There's a different question, which is around like the sharding of data, and our take on that is that at this point, we don't need to shard. We have tested, up to 128 megabyte blocks, and we can generate commitments for that. And so it's kind of a future problem if we ever have to shard the publishing of the data. It's kind of a separable problem. And then separately from all of this is how do you, as an individual client who doesn't want to download all of the chain data, how do you know that it's being published correctly? And this is where the light clients come in and data availability sampling. And Sriram is totally right that any blockchain that has a commitment scheme, erasure-coded commitment scheme, can support data availability sampling. We have actually built this, of course, and so there are probably some implementation gotchas that may happen.
Kudos to Avail for doing it. I think it's a great public resource.
Thanks. Yeah, and what that allows is as a client, like either a protocol component or an individual client, an application running on the end user's machine, you can actually be sure that the chain is publishing data correctly without downloading all of the data. In the case of Avail, with the KZG scheme specifically that we use, you can do that without using fraud proofs. You can independently come to a conclusion that is available. Furthermore, these light clients are actually networked between themselves. So they actually form a second separate network from the publishing network. They have their own DHT, distributed hash table, between them. And as they sample, so each individual client only samples a few times per block, but they put that data that they sample into the DHT. And that allows, as a whole, the cloud of light clients forms a replica of each block. As each block is published, it's kind of like BitTorrent, if you've ever used BitTorrent or kind of seen that in the past. It's a little bit like that. But it happens, every time a block is published, it kind of gets copied over onto the DHT of the light clients. And that adds what we call high data availability. We just made that up, but it's basically like this idea that we're actually creating a whole new replica, such that if the publishing side of things, was out of reach for whatever reason, the light clients can still communicate between themselves and know what was the final, truth accessible to them. So yeah, anyway, what to do?
Yeah. I know I've seen a lot of threads on Twitter, data storage versus data availability, and we're not going to ask what's the difference, but I used to work for a data storage protocol, so I'm very curious if you see this as a distraction, or if you see actually use cases, if you see that there is maybe a future of data availability adding data storage, or how do you see these two different components?
Oh, I can take it. Data storage is, the reason data availability or data publishing is super security critical is that if you're running an optimistic system, then your safety, whether your funds are safe, depends on the data being available, because somebody has to actually download the data to challenge you. If you're running a ZK system, if you don't have the outputs of the computation that the sequencer made a claim for, even though you know the computation is correct, if the sequencer goes offline or refuses to publish future proofs and so on, then nobody else can pick it up. So you're extremely reliant on the single sequencer to continue the functioning of the system. So data availability, which is basically a short-term property, you have a term limit, let's say 2 weeks. You want to make sure that the data remains published and available and retrievable for those 2 weeks, is super, super security critical. But data storage, which is, are there at least one node which has a replica of the data, is not that security critical. But it is important to have an archival view of all the transactions that happened. So what we will see is examples of systems where you want archival access and examples of systems where you absolutely don't want archival access. Imagine you're running a game tournament where like many agents, players are playing games, or maybe even AI agents are playing games, and you want to have the results of these who won the game to be verified and available on chain. And what is important to be persistent is who won the games. That needs to be persistent. Not every move every player made in every game ever happened in the history of blockchains need to be available. So long-term data storage, what will happen is some of the systems that use short-term data availability systems will subscribe to other long-term data storage solutions to actually archive these data and have a history of transactions available for a much longer period, maybe even perpetually. So we see these as complementary solutions in the stack. And since storage doesn't need that much of security, you can use different kinds of trade-offs. You just, you instead of slashing people for not storing data, you incentivize people to store data. You can do all kinds of interesting trade-offs there. There's also the thing that when you want to make a system which is making claims that it's incentivizing or storing data for the long term, even perpetual term, you need to make sure that the system handles churn, nodes coming in and going at a very high rate, because nobody is going to remain in the system forever. Whereas in a short-term data availability system, you have the same nodes which actually downloaded the data will be around for the couple of weeks. So these are the different trade-offs between these two kinds of systems.
Yeah, I think I would mostly agree with that. And I think one of the nice things about data availability is, well, I don't care. Not every node needs to know or cares that all the data is available, or you only care about your individual transaction, your individual part of the state that it's available. But basically, data availability allows you to sort of join forces and collectively you help each other ensure that all of the data is available, and in particularly it's also recoverable. So I can retrieve it. And we sort of, at Espresso, we're building a shared sequencer, and we sort of see, I think, Sriram, you alluded to this, the amount of total bandwidth that is available in the system is actually huge. So I think data availability will become a commodity, which is amazing, right? Like this will help blockchains scale to sort of limits we haven't seen before. And so we provide sort of a data availability solution that looks, fairly similar to something like EigenDA, as part of the Espresso sequencer. So you pay some sequencing fee that is proportional to the amount of data that you're sequencing, and included in that is the DA solution. But you're also very much free to use an additional DA solution. So you can also use any of the other DA solutions itself, or if you want to post the data on Ethereum, you can also do that. And one of the nice properties there is that the security is, okay, the cost will, you have to pay for each of them, but the security is additive, right? So if you post your data to many DA systems and one of them goes down, well, it's okay, because all you need is one place where you can recover it. So I think, that's a really, really nice property of DA that's sort of been underappreciated.
I love it. I love what you say. Data availability will become a commodity. I like it. I think it can be a nice tweet. I think. I don't know how much time we have left. 5 minutes. Okay, I work for Hyperlate, so I need to add something interoperability. So we are an ABI's partner of EigenLayer. We're a launch partner of Celestia. So I'm curious how you see interoperability. Like, obviously, you're working with us, but is there also a path of future where you're gonna, you might, do it in-house? You might do it. We don't know. Like, what's your view? Is it like other projects that need to take care of, other roll-ups, or is it something that Celestia can take care of it?
Sure. I guess I'll start talking about Celestia. I mean, the Celestia. I can't really comment on the future of what the Celestia protocol will change into or support, because it is a protocol that is live and is governed by its community, not by John, unfortunately. I'm not the sole dictator to the Celestia protocol. So if the community wants to add and enshrine to the protocol certain features that support interoperability between rollups and improved bridging and stuff, then it's up to them to decide to add that. With respect to my own personal views on whether or not these kind of additional features should be enshrined into the protocol, I would say no, because one of the nice properties about Celestia is how minimal it is. That it's very, very cheap to verify the state transitions because they're extremely minimal, and the more features you enshrine into the protocol, the more expensive and more complex to maintain that will become. So in my view, these kind of interoperability issues, which are issues and do require some project to solve them, should be solved at the appropriate layer, which in my opinion is the layer in which the things that need to interoperate reside, which is the execution layer is on top of the data availability layer.
Yeah, I think sort of as Espresso, I think interoperability is we view interoperability as hugely important, right? It is, I think Ben alluded this this morning in his remarks that sort of blockchains or Ethereum, it's about the unity, right? It's about the composability. It is about the interoperability. And I think we'll have a panel later on shared sequencing, and this is sort of the core thing that we work on is shared sequencing, which can help interoperability solutions. And why can they help? Because one of the reasons is that you can sort of then as a bridge, you can know that if two rollups are sequenced together, I know that the state transition is final, so I don't have to wait 15 minutes until things are posted to Ethereum, until the final state transition is posted to Ethereum. I can bridge significantly faster, and I can, there's a ton of other interoperability benefits that come from sharing a sequencer. So yeah, I think interoperability is key, and we're very much working on trying to enable better interoperability solutions.
I'm very glad you asked, because Avail is actually an infrastructure layer for helping modular execution layers to scale and interoperate. And we've been talking about DA thus far, which is one of the 3 pillars of Avail. But we also have a product that we're launching this year called the Nexus, which is all around unifying ecosystems across Web3. And the way that works in the Avail view is it's a proof aggregation layer that also relies on data aggregation at the DA layer. So we're leveraging our DA layer and combining it with a proof aggregation layer on top that is then able to provide very strong guarantees about the state of any rollup that is in the system. And the reason that we're doing this is that with this rollup-centric roadmap, as I was saying before, and I think is abundantly clear, there are tons of rollups already in existence and many, many, many more coming. And so interoperability becomes a huge issue. Fragmentation becomes a huge issue. Liquidity will be fragmented. Functionality will be fragmented. It's already a pain. If you need to transfer something from one L2 to another L2, it's horrible. If you want to write an application that uses multiple chains, is a total disaster, basically. And so given how bad it is today, like, it's not going to get any better if we just keep adding chains and don't come up with solutions to make things work together. And so that's essentially, you know, what we're trying to solve. And finally, in order to secure all of this, we're adding a security layer to the Avail DA called Fusion Security, where we will allow tokens to be brought, like high-value tokens like BTC and ETH, to be brought to Avail DA and have them participate in the consensus of Avail DA. And so that provides like a complete stack that is still modular. All of the chains in the system are still independent, but we allow them to work together. And we allow developers to write applications that use all of them in unison. So that's kind of our vision for how, you know, things will work together.
A quick question, Dan. Does Avail also have shared sequencing? Or like you can only publish blobs to Avail?
Yeah, we do have plans to implement decentralized sequencer selection. So we won't do the sequencing, but that is part of the Nexus as well.
But people can write only blobs to the Avail chain, or they can write like small transactions?
Yeah, these are separate layers. So the Avail is completely agnostic as to what runs on top of it. And you can think of the Nexus as a sovereign rollup. It itself is a sovereign rollup on top of Avail that ingests ZK proofs from around Web3, verifies them as part of its own ZK VM, and also does data availability sampling to Avail to guarantee that the data is at the DA layer and then produces an aggregate proof that can then be consumed with all of that. So then any rollup that consumes this aggregate proof can also do DAS and then be highly assured that of the state of all of these rollups. So the vision that we have is one of asynchronous composability. We think that there has been too much focus on synchronous composability because this is what, you know, blockchains have provided up until now, and there are still some, you know, very valid use cases for synchronous composability, like flash loans and whatever. Like there's some DeFi use cases like that, but there's so much more that you can do asynchronously. Not more that you can do, but just that there's just so many things that can be done asynchronously that don't need synchronous composability. If you look at the internet today, basically every application you use, if you pull up your phone, every single icon on it represents a whole host of asynchronous services behind it, right? You go to Amazon, you click buy, Amazon is doing like, you know, 30 things behind the scenes, talking to their own payment service, which is a separate asynchronous service, talking to some other payment service, there's another payment service, talking to their warehouse provider to find out if the item is in stock or whatever. So all these things are asynchronous. They don't need to happen all, you know, in the same machine in RAM together, right? So that's my soapbox.
Awesome, thanks, Dan. When you're thinking about interoperability, I think there are two dimensions. One is the temporal aspect. Is it happening together? Are these two transactions like synchronous or asynchronous? So that's one dimension. You know, what is the time scale at which things can happen? Can they happen atomically or they happen non-atomically? The other axis is the trust. What do you need to trust to actually make the interoperability system work? And you know, there are all kinds of trust models here. Like the simplest trust model is trust some intermediate zone. You know, the zone basically guarantees that both, you know, the thing was done on this side and on the other side. Okay, that's one example. Or you could have an interop solution which is secure as long as both the zones are themselves secure. I'm bridging from chain A to chain B, and the interop solution is secure as long as chain A is secure or chain B is secure. And even more rigid than this is a solution where it's unconditionally correct interoperability. And unconditionally correct means, both of these chains are themselves in some kind of a common zone. They all use, for example, both are roll-ups of Ethereum. Then there is no state in which there is an incorrect state from chain A which has been bridged to chain B. And so these are levels of interoperability, security in interoperability, and there is levels of synchrony and asynchrony. And when we are thinking about this chart, there is all kinds of complex operating points. But one important thing is something like Espresso, which is a shared sequencer, combined with some kind of a ZK-proof system can actually allow you synchronous high trust interoperability. So that's one of the operating points in this. But in general, you should only pay for synchronous composability when it's worth it. Like Dan mentioned, most solutions in the internet are asynchronous. And if you can create a system where you can pay for synchrony when needed, and in the other times, so this is, you can think of as systems that have synchrony on demand rather than enforced synchrony. I think, the Espresso guys have some cool designs there, so maybe they can talk about it.
Well, thank you very much for the pitch. I like that. No, I think that's, it's a very good point, is that, one of the benefits or the whole idea of roll-ups is that, the layer 2s is that they horizontally scale Ethereum. And we want to maintain that, right? If we run everything as one massive chain, okay, then we have Solana, and we have dropouts every week or so. I don't know, but that doesn't work, right? It works to some point, and then you pay for it by having less security, by having less reliability. But if you can have a system where sort of every single component works on their own, but then when you need to have composability, when you need to have sort of interoperability, you can still have that, and you need to pay for it a little bit, but you can have that, then it creates a better system all around, I would say.
Yeah, well, thank you so much, guys, but unfortunately it's over. We are running a little bit out of time. It was a pleasure having you, and yeah, thank you.
Thank you.
Thank you for having us.
Thanks so much, everyone.
Thanks, everyone.